Good morning. This is very exciting and unusual for me, so I wrote words on a page and I'm going to read them. I'll read everything so I don't improvise. Good morning. Welcome to the first session of WACT 2026. We are extremely lucky to start our journey with Avi Wigderson. Avi is one of the founding fathers of the theory of computing. He has important and fundamental contributions to all areas of theoretical computer science, and he has been shaping our field to what it is today. Avi is currently the Herbert H. Mass Professor in the School of Mathematics at the Institute for Advanced Study in Princeton. His works were acknowledged by many prizes, including the Nevanlina Prize, the Gödel Prize, the Knuth Prize, the Abel Prize, and the Turing Prize. He has been collaborating with more than 100 researchers and has been a mentor to an outstanding number of researchers, including myself. Avi wrote the book Mathematics and Computation, a theory revolutionizing technology and science. This book gives a front row seat to an amazing story and a beautiful mind. Avi's curiosity is infinite. He is interested in tiny puzzles as well as the most complicated webs of ideas. Today, he is going to tell us about a pair of non-identical twins.
Hi, everybody. Thank you, Amir. All right. Thanks. So I'm really happy to be here. It is too loud, too soft, everything good. Do you hear me? Yeah, two identical twins. So I'm going to tell you about the permanent and the determinant from many, many different points of view. This is the bicomplexity workshop, and most of you, I think, are in this workshop. So to many of you, some things will be familiar, but a few maybe not so familiar, and I hope to at least get for everyone something they didn't know. If you knew everything about it, tell me afterwards. I like to add stuff. Okay, there are twins. We think we fix a field, characteristics different than two, and matrices over this field and by matrices, and then we have these two polynomials. Not too far. Oh, is the battery? Okay, good. We have these two polynomials. The determinant is the most familiar one, and the permanent is the same sign, the same thing without the sign. They are homogeneous, multilinear degree polynomials in these n-squared variables with simple coefficients. They look very much alike, and they are not. I don't know how many people saw this movie. They are as different as this guy. So I'll give you a couple of slides of overview of what we'll see throughout the talk. I hope I get my 55 minutes. I'm going to stand here and to do that. Okay. Yeah, so lots of different aspects of the differences as we see. Can you find I have a different? That's the thing. Yeah, so from a physical point of view, maybe I'm familiar, they represent different types of particles. We'll talk about that. Different knot invariants represented by, one by determinant, one by permanent. They are used in many different contexts, but separate for both. For determinant, of course, capturing linear algebra. In geometry, it appears as computing volumes, and really it's all over the place in mathematics. The most familiar is used polynomials in mathematics. The permanent is used for enumeration. We'll see that in statistical mechanics, and absolutely fundamental in computational complexity. And I'll talk, I saw the Shrikant's introduction. I'll try to make good on some of his promises about the connection between algebra and complexity. As I mentioned, counting, permanent counts lots of things, but also the determinant can count few things. We'll talk about that. The main difference is the complexity. The determinant is easy to compute. We'll see how easy, and we believe that the permanent is difficult. This manifests itself, maybe I'll just stand here and press buttons, and then I'll know what. Both in Boolean complexity and in arithmetic complexity, and there are completeness results which I'll explain and talk about. It's really their appearance everywhere in the appropriate context that makes them so important and complete. Where do they sit? So we have the usual dichotomy between easy and hard problems in Boolean complexity, between P and NP, and NP complete problems. And this polynomial sits somewhere, determinant below P and permanence above NP. More precisely, if these are the sum of our many complexity classes organized by inclusion, the determinant sits close to log space or NC, and the permanence sits high up between PH and P space. We'll also talk about quantum computing, so it's above what good quantum computers can do. That's a Boolean story. In the arithmetic story, we have these classes VP and VNP that I'll define analogs of P and NP for the arithmetic case. Okay, I'll start with algebraic computation, a very basic introduction, which I'll go through fast. The basics are, again, we are computing things algebraically, so the two models I'll talk about are circuits with plus and times over this field, and formulas which are just circuits that are trees. In the same way, each of these things having plus and times and variables and constants in the field, we are computing polynomials, so this is all about computation of polynomials for now. A very surprising, I would say, connection between these two models that we believe in the Boolean complexity world to be very different from each other, exponentially apart. Here they are quasi-polynomially close, so I will not distinguish formulas and circuits. The first class, VP, is all easy polynomials, all polynomials you can compute in polynomial size. And Valiant was the first to investigate this arithmetic analog of P versus NP and introduce these classes, asking the same question as in the Boolean case: can we compute everything we want to? So everything we want to, maybe all possible polynomials of some degree. I'll only talk about polynomials whose degree is polynomial in the number of variables. That was Valiant's very good insight. And I mentioned that VP will be the easy, the class analog to P. And so what are all polynomials we may want to compute? In this class are many familiar ones that we can do: determinant, discrete Fourier transform, symmetric polynomials, multiplying matrices, and so on. We know that there are hard polynomials, like a random polynomial is very easy to prove, is by a dimension counting argument that does not have a small circle. But random, we don't expect to be able to, we don't care so much about computing random polynomials. We want to, what do we care about? Which polynomials do we want to compute? You have to define this, like in NP. In NP, it's something we can verify. In the arithmetic case, Valiant defines VNP, which is supposed to capture the analog. I will define it soon, but it contains lots of polynomials capturing counting problems. They appear in statistical physics, as I mentioned, and the permanent is one of them. So we have this class VNP containing VP, and these two polynomials turn out to be complete for these respective classes. This what Valiant showed, and I'll even show you a proof of one of these, the easy one. I'll have a couple of small proofs here, those for which it's may be too fast because of notation. It's not very important. It's just nice that sometimes there are simple proofs you can give in a talk. So what's the complexity of determinant? I mentioned it was easy. How easy? There's a polynomial time circuit, so polynomial size circuit for determinant. And when you ask mathematicians, they will tell you this. Yeah, there is an efficient algorithm. And I say, yeah, how do you do it? Well, you do Gaussian elimination. I said, but Gaussian elimination has division. And then they think, and they don't know how to do it efficiently without division, but it can be done. So I should show this, and there are simple algorithms that can do this. What was more surprising, led to the result I mentioned before, is that actually you can have small formulas for determinant, namely small depth, log square depth, formulas for it. I'll mention many open problems, and one great one is whether it can be done by polynomial size formulas, namely by logarithmic depth circuits. I don't think everybody believes the answer is no, I think, but we don't have really good evidence. So Valiant shows that it's complete, so now we'll talk what complete means. If you have a formula of some size S, then there is a determinant for the polynomial it computes. Okay, the determinant of a matrix whose size is basically S by S. So there should be a matrix corresponding to this polynomial, and the determinant of the matrix is that will give you this polynomial. I mentioned this in green, that mathematicians are studying determinantal representations of polynomials in more specific manners, and to most I talked about this general theorem was unfamiliar, this completeness. It's so simple and beautiful that I'll show you the proof in 1 minute. How do you prove that something about formulas, anything about formulas? You do induction on its structure. It's a very simple structure, n's and s, or pluses of times and so on. So we need a matrix whose determinant is a polynomial computed by the formula. Well, a formula is either the sum of two formulas or product of two formulas. If you had a matrix for G and H, you want a matrix for G times H, very easy. You put them next to each other like this, and the determinant will be what you want. So that's very easy, and then you think how to do addition, and most people I know, including myself, get stuck. But it's really simple if you know what's the right induction assumption, as usual. So you decide that your representation will be almost triangular. So there'll be ones in the one below the diagonal and then zeros below that. You postulate it. And so this construction works, except that they're missing one here, but you can always add the one. So we are done with multiplication. Of course, now that we added this condition, we need to fix the induction assumption. It cannot be a 1 by 1. It will be a 2 by 2 matrix for every variable or constant like this. So why does it help doing addition? Because of the following. Do as if it was a multiplication problem, and then add a row and column with these very specifically located ones, and the rest are zeros. What this does, if you just expand according to the, let's say, top row, is you realize that one of the ones will pick the determinant of H, and one of them will pick the determinant of G. And this really solves the problem, except that it doesn't have the structure we want. We have a 1 on the lower triangle, but this is also easily fixed by switching this row and column. Anyway, if you didn't follow it, doesn't matter. There's a cute, simple proof that Valiant gave of this fact, completeness of determinant. What about the completeness of VNP? I didn't even formally define VNP. It's much more complicated, but it shows that, well, first of all, let me define it. One of the definitions is that polynomial is in VNP. In Boolean complexity, functions in NP can be easily verified. You can see that a good analog will say that for every coefficient of the polynomial you care about, there's an efficient algorithm to determine what this polynomial is. This is like the certificate. So that's the definition. That's over Z, and you can define it over any field. It captures all explicit polynomials. Certainly, there is a description. If there is a circuit computing every coefficient of every monomial, you can describe it in polynomial size. Valiant shows that in the same sense, by projection of the type I showed you with the determinant, happens for permanent. There is, for every polynomial in VNP, there is a matrix whose permanent is that polynomial. So completeness in the same sense. The proof I will not show you. Of course, like P versus NP, we want to separate them, and there are many ways to go about it. How do you go about separating VP from VNP? Well, now we have complete problems. All we have to do is that permanent is harder than determinant, right? So harder in what sense? In the same sense we did reductions before. You want to show that there is no affine map or projection, which I call good map here, that maps permanent to determinant. In other words, I ask you to compute the permanent of the matrix. The question is, what is the smallest size? Let's say an n by n matrix. What is the smallest size of another matrix so that you can plug in the variables in the bigger matrix, let's say of size k, a function of n, so that the determinant of the new matrix will be the permanent of the old one. Here's an example, was already studied by Polya. The permanent of this 2 by 2 matrix is really the determinant of the one next to it. You just flip a sign. That's very easy. So k of 2 is 2. We want k of n. Valiant actually shows that first of all there is by permanent being in VNP, really there is always an upper bound that's exponential. So it's a doable problem. The question, what is a function? The best lower bound we know is a quadratic lower bound, which if you think about it is really a linear lower bound because there are n squared variables. But still, it's a beautiful, non-trivial proof. One line. or 5. And the VP versus VNP question is very canonically simply phrased as just prove that this number, k of n, goes superpolynomially with n. So that's one way of separating VP from VNP. You try to do this, and then it doesn't work, and you look for techniques and tools. And one of the most famous and elaborate one is the so-called geometric complexity theory method that uses the representation theory and algebraic geometry. It is based on the fact that both determinant and permanent have symmetries you can easily think about, and these symmetries actually define them. So you can study this from the point of view of these fields and look for obstacles of mapping a permanent to a determinant that's too small. This has gone a long way and definitely suggested avenues in algebraic complexity theory that are very interesting. At this point, I think I would say it's stuck. It's not hopeless, but it's stuck. we'll talk about, I called it number 1 because I have number 2 soon. We do know some lower bounds for these polynomials, but they are restricted. That's what we do in complexity theory. If we demand that we are talking about non-commuting variables, so far variables were normally commuting, then we have exponential lower bounds on formula size. So in the non-commutative world, we don't have this relation between formulas and circuits. There is exponential lower bound on formulas, and we have no idea how to prove super polynomial lower bounds for circuits. It's a great open question. You can study another model, multilinear computation. Of course, both these polynomials are multilinear. Every variable appears with the power 1 at most in every monomial. There's n to the log n lower bound, so super polynomial, but not more. It's a great open question to prove a bigger lower bound, in particular exponential one. And if we restrict formulas and circuits to constant depth, we have this wonderful lower bound of Gupta et al. Showing that at depth 4, the determinant needs really exponential n to the square root n lower bound, and it doesn't get stuck there stupidly. It gets stuck there because this is the right answer. There are upper bounds of the same magnitude coming from the depth reduction technique. So this is tight. Of course, or not of course, but it's easy. The same argument applies to the permanent itself as well. Almost every lower bound that applies to determinant applies to permanent. But here there is room for improvement, and the point I want to make is that any improvement here will separate determinant and permanent. For a long time, we didn't have any truly, super polynomial lower bounds for even depth 3 circuits, and this was resolved with this paper of Newton and Shrikant and Tavenas. We have super polynomial lower bounds, but for any depth d actually, including 4, but it's not strong enough to resolve this question. Okay, these are restricted lower bounds. I want to move to describe really what makes this whole story special. I think that complexity theory was extremely poor before the permanent showed up, before Valiant put it, in our faces. Because it has lots of nice properties. I'll tell you 2, and then we'll see a third one, and we'll see the impact of, these properties. With hindsight, we understand more, and we understand that polynomials of low degree are error-correcting codes and stuff like that. But I think that the complexity world was focused on Boolean computation, and this totally revived it, and in fact several times over. So this is a connection Shrikant was mentioning between algebra and complexity. So what do we know about this? Polynomials are polynomials over matrices, and they possess what's called downward self-reduction. So we can reduce a problem of size n to several problems of the same type of size n minus 1. How? This is simply row expansion, right? You just expand the determinant or permanent in this obvious way. So you reduce the size n to n copies of size n minus 1 matrices. And this is very fundamental. We can reduce the size, even though we lose from 1 to many. We'll see how to handle this. Another very important property is a random self-reduction. So you can reduce computing the permanent on an arbitrary matrix to computing it on a bunch of random instances of permanent. How do you do that? I'm sure many have seen it. Suppose you have a circuit that computes the permanent almost everywhere correctly. It makes an error only over, let's say, 1 over n. Assume it's a finite field, so 1 over n makes sense. You use interpolation. So you want to compute it at x. You find you draw at random another matrix y, and you look at the line through x and y in this space, and you define this polynomial in single variables that computes the permanence on this line. Now, every individual point in this line, because y is random, every individual point is totally uniform in this space. The probability that you make an error there is small, 1 over n, 1 over 10n. And so you will not make an error on g of 1, g of 2, g of 3. You pick up n plus 1 point. If you didn't make an error, this happens with high probability, then you can interpolate this polynomial and get back the g of 0, which is the value you wanted. So what happened here? I should point out you can do it even if the error was 1/3 using error correcting tricks. You don't need the linear error. Constant error will be fine. So what does it mean? It means that you can make the permanence harder than it was in some sense. If you could compute it on most inputs, you can compute it on all inputs. Or put differently, if it's hard in the worst case, you immediately infer that it's hard on average. That's a very powerful statement. Worst case and average case are the same for the permanence. And this, of course, as I mentioned, works for any low-degree polynomial. It's the source of what's called arithmetization, turning Boolean functions into polynomials and studying them, which has been extremely impactful in complexity theory, and I'll give some examples of such important implications. To lower bounds, to the randomization, to probabilistic proofs, they are listed in reverse chronological order, and that's the order I'll present them. For lower bounds, I mentioned another avenue of attacking the VP versus VNP problem. This is called the algorithmic approach via the problem PIT, polynomial identity testing. What is it? I can represent it as a question about determinant because of variant completeness. So the input is a symbolic matrix. Thanks. The input is a symbolic matrix, namely a matrix having entries which are 0, 1, and variables. And we look at the polynomial in these variables that is the determinant of this matrix M. So this polynomial, call it P. So what we want to know is whether this polynomial is identically 0 or not. There's an obvious probabilistic algorithm for this problem, starting with the Miller-Lipton, Schwartz, Zippel, Dovas, and others. It's very simple. Of course, determinant of a symbolic matrix you cannot do Gaussian elimination for, but you can plug random values to these variables, and then you have a numeric determinant for which you have an efficient algorithm. Of course, if the polynomial was identically 0, it doesn't matter what you plug in, you'll get 0. If it's not identically 0, then the variety is very hard to hit, and you'll miss it almost surely. So it's a very good, simple probabilistic algorithm. There's a question that was asked actually outside complexity theory by Jack Edmonds from the point of view of combinatorial optimization. He asked the question if whether this polynomial, the determinant of a symbolic matrix, has a deterministic polynomial time algorithm. It was not clear how fundamental this problem is for a long time, but it's absolutely fundamental. It asks for a de-randomization of a probabilistic algorithm, a single one, not all of them. And the year 2000, this sort of shocking result was discovered by Cabanes and Impagliazzo, saying that if you can de-randomize this particular algorithm, find any polynomial time algorithm for this problem, PIT, then you have separated permanent and determinant. I put it in quotes because the statement is more technical, but that's the message you should get. And, you know, for people who never saw this, it's sort of shocking for several reasons, but I think the most obvious one is that you want a lower bound, and you achieve it by finding an algorithm. It's not clear how this works. I could explain, but I won't. The point I want to make is that this uses fundamentally both the downward self-reducibility and the random self-reducibility. It's absolutely crucial for this result, and we'll see for other results as well. Anyway, many have tried this algorithmic approach. One thing we can do, trying to make our life easier, is to move to the non-commutative world again. And it turns out that if the variables do not commute, then this non-deterministic version of PIT actually has a deterministic polynomial time algorithm. It doesn't have one algorithm, but now we know 3 or 4 really different ones in these references using very different techniques. And the one I was involved in with Gar Gurwitz and Raphael here leads to really interesting things in we call geodesic algorithms, generalizing the convex optimization techniques from Euclidean space to Riemannian manifolds. It connects very strongly with invariant theory and the geometric complexity theory I mentioned before. It still doesn't tell us anything about the problem we wanted to solve, the commutative case. So more applications of these nice properties of the permanent. Hardness versus randomness is paradigm that we study randomizing general algorithms. What's the power of randomness in probabilistic algorithms? That's a basic question that we keep returning to, and so I was fascinated with all my many years in the field. We know that probabilistic algorithms sit somewhere between p and exponential time, and one result I had with Noam Nissan, what is based on what's being called the NW generator, is if you have strong enough lower bounds, then randomness is weak. If exponential time does not have polynomial time circuits, then BPP can be strongly de-randomized. This is sub-exponential time. This was, of course, strengthened, but I like to state it in this form. You can save non-trivially in de-randomizing any probabilistic algorithm. But this has something is unsatisfactory here, right? The assumption is non-uniform. You assume hardness against circuits, and you get a simulation, the randomization for uniform circuits. What about uniform assumptions? Suppose you just want to assume that no Turing machine can solve exponential time problems, let's say, in probabilistic polynomial time. So the analog assumption was uniform. It took a decade, and Russell, Impagliazzo, and I proved the same consequence. Almost the same consequence is something essential you have to add, that you get BPP, the randomized algorithms coming, having a non-trivial simulation on average, in the sense that no efficient algorithm can find an input for which there is an error. Anyway, this took a decade. There is even a section in this paper asking why did it take a decade for this analogous result to come, and the answer is we understood a lot about downward and random self-reduction of the permanent and how to use it in different ways. Anyway, but that's another important consequence of the properties of the permanent. Yeah, so I mentioned that. Now I want to move to the, again, you all know this, or many of you know this, the most important consequence of these properties of the permanent. It led us to the understanding of interactive proofs. What are proofs? They are all about efficient verification between a verifier that, is efficient algorithm but is skeptical, and an untrusted, all-powerful prover. NP really captures this setting completely only for recent proofs, like paper journal proofs, where we verify, something that's written down. Interactive proofs are the analog where we allow randomness and interaction, and we accept a tiny probability of error. We allow the verifier to ask random questions, and just want to make sure that he doesn't make, or she doesn't make an error with more than a tiny probability. This definition of interactive proofs, and in fact many versions of interactive proofs, is of course all over the place with important consequences in both science and technology and math. I mention here the main ones. The ones, it was defined, was studied together with these very magical properties I mentioned, led to a really magnificent story and set of results about the power of these probabilistic interactive proof systems. They all use, again, I just repeat this again and again, these properties of the permanent, and I don't know where it would be otherwise, because Noam Nissan heard about this random self-reduction. I don't know where I had this result written down, Lipton and Beaver-Feigenbaum, random self-reduction that I showed you, and realized that you can have a proof for the permanent in multi-proof or interactive proof system, and then in a couple of months came this paper with Lundfors and Karloff, putting it already in single proof or interactive proof, and followed by Shamir's result that's really IP equals P space. The same, almost, short time after came this complete understanding of what multi-proof proof systems can do. They can do exactly non-deterministic exponential time. And this, again, was scaled down and refined and led to the famous PCP theorem, which characterizes NP. People started defining quantum interactive proofs. These have stars in them. With one prover, they don't add any power. With two prover, again, absolutely shocking results that multi-prover quantum interactive proofs can convince someone, an efficient verifier, of problems that are not even computable. It's sort of stunning results with many consequences in mathematics that I will not go into in this talk. I want to say something about the way these properties are used in the proof of permanent being in having an interactive proof. And for this, we need another version of this random self-reducibility, a variant or a new one, basically this one. We saw already that we can compute one input of the permanent from many either smaller instances or random instances. We'll use smaller instances. But I want to show you now how one can verify this. Wow. Somebody kicked something. Verify the values of many permanents from just a single one. So it goes in the opposite way, somehow compresses many into one verification, and of the same size. That's very important. It looks very similar to what the interpolation we used on a line. Now it will be on a curve. We want to certify, somebody claims that the permanent of x1 is a1, permanent of x2 is a2, and so on, for k matrices. And we want to check this by checking one permanent. How do we do this? So here are these points. We pick a random point like before, like this y, xk plus 1. And we pass a curve of low degree, of degree k, through this space, just like the line before, but it's a curve of degree k because we have k plus 1 points to interpolate through. It's still a low degree polynomial. And now we pick one random point in this low degree polynomial, on this low degree curve, and ask the verifier, the verifier asks the prover to give the permanent of this polynomial, the single parameter polynomial. Now it will be of degree, I guess, k times n. It's very easy to see that with very, very high probability, it depends on the size of the field, one of the size of the field roughly, the verifier will have to give the correct answer if he committed himself to the values of all these permanents. So now you have a way to reduce one problem to many that are smaller, and then we can take all these many smaller ones and reduce them to a single one of the same size. And this led to the so famous Lund-Fornau, Karloff and Nissan paper. How do we, check the value of a permanence of an n by n matrix with an untrusted prover? You want to know there's a claim about the permanence of particular matrix, and we do what I just said. We compute a sequence of matrices of smaller and smaller sizes using this alternation. You make many small ones, compress them into a random one. And so you produce them, and you just keep asking the prover to give you the values. But in each step, if he was correct currently, then he was correct in the previous claims with very high probability. And of course, the last one is one by one matrix. You can do the permanent yourself. So that's in one leg, the LFKN protocol. Again, using the same very important properties. Okay, so I'm more or less done with the coverage of the arithmetic side of things. Of course, there was a lot of Boolean consequences to Boolean functions and normal complexity classes, as we just saw. I want to talk about some few other aspects that are mainly from the Boolean side. So now we are back to evaluating functions rather than polynomials. Valiant, in a parallel paper to his arithmetic one, talks about Boolean computation in this other paper, same year, and defined a class Sharpie, this class of counting problems. He wanted to understand, again, we are looking for the natural ones, the natural counting problems. There are plenty of counting problems all over the place in computer science, in statistical physics, in algebra. For example, we may want to count the number of satisfying assignments of a formula. We may want to count the number of clicks in a graph, number of Hamilton cycles in a graph, number of perfect matchings in a graph, which is a permanent function, number of linear extensions of a poset, number of spanning trees of a graph, etc., etc. They're all counting problems. And I put a line here because that's the line separating, if we think about them as decision problems, right? These are counting versions of decision problems we are all familiar with. That's the line separating those that the decision problem are in P versus being NP-hard. And the question is whether the same dividing line happens for counting problems. One would imagine the answer is yes, and one of the, again, revelations by Valiant in this paper is that the answer is no. So, in general, you can define Sharpie simply to be the number of accepting paths in an NP machine. Of course, all of these are examples. And you wonder which are complete problems, which are hard problems in this class. Note the linear extensions of a partially ordered set. The decision problem is trivial. The answer is yes. You can always extend it. So, some look very easy. Turns out that those I checkmark are Sharpie hard, are really hard. And the really shocking one was this. It's a permanent. We can easily check if a graph has a perfect matching, but counting them is as hard as counting the number of clicks in a graph. That was really fundamental and important and consequential. This is true also for a number of linear extensions. It's not true for spanning trees. This can be reduced to determinant. But it's true for lots of things we really want to count in all these fields I mentioned. There's another nice exception which will be relevant, is counting the number of perfect matchings if the graph is planar. Turns out that physicists who cared about this, because they care about grid in 2 dimensions, that's planar. This can be done in polynomial time, again, by reduction to permanent by Castellan. Okay, so it's definitely a different story. Counting is different than decision. This led to all sorts of results. I mentioned this before. The easy ones, and they are special. They are reducible to determinant as opposed to permanent. The class sharp P is understood in terms of completeness, but I want to add a higher level note. Igor Park is here. I'm not sure what he will talk about, but he gave a beautiful series of lectures last year at the Institute. And there's a conceptual contribution to algebra that we have here. I'll give you an analog. I think that it's an old understanding, an import from computer science to mathematics, is a question of what's an explicit construction. People in mathematics like explicit constructions as much as we do, but when you ask what is an explicit construction, there's no formal definition. Tell me your construction, I'll tell you if it's like pornography, right? And the famous, I forget the name of the judge. But we came along, and by now it's well accepted that an explicit construction in most contexts is something you have a polynomial time algorithm to describe. So an analogous happened more recently by Igor and Greta Panova and others. What is a combinatorial proof? So in enumerative combinatorics and related fields, there are proofs of various identities, combinatorial identities. Some of them are directly combinatorial, if you look at them. Some are more mysterious. They involve subtraction or division, which are not so natural. And the question is, what is a combinatorial proof? Well, here's an answer. It's not my answer. I think it's Igor's answer. Would be if you have a reduction from the permanent, then it's a combinatorial construction. And they have beautiful results about examples where it is possible or it's impossible under assumptions like the ones we use, like the hierarchy doesn't collapse. So that's another import of this study of permanence. Okay, one more context which I want to mention what I talked about in the beginning. I want to tell you somehow how this study of determinant and permanence relates to physics. So just a short introduction to quantum mechanics, 2 lines. We have randomized algorithms, extended deterministic ones, and now we have quantum algorithms extending probabilistic ones using quantum mechanical operations in the algorithms. This was suggested in the 80s by Feynman, by Manin in Russia, and so on, and was formalized within computer science. What is a quantum Turing machine? What is a quantum circuit? And so on. And it was quickly realized that this sits, as I mentioned, between the hierarchy and P space in this class, P to the sharp P. So Turing reductions to sharp P. We know the famous Shor algorithm that shook the world and showing that current foundations of cryptography are actually broken by efficient quantum algorithms. And so, of course, lots of efforts are going to building quantum computers and to building stronger foundations for cryptography. But the interesting story is that physicists have been studying determinants and permanents for their own sake, and in fact, I'm quoting things that I cannot really explain to you, but the world is made of two types of particles, right? The fermions, which are capture particles conveying force, and bosons, these are, these things, or what we are made of, and so on, bosons. And, they live happily with each other, and they make our world go. And it turns out that if you have n independent identical particles of the first type, fermions, then their joint wave function is described by a determinant. And if you have an identical bosons, then their wave function is described by permanent. This determines their behavior, what happens when you measure them, and so on. And it's sort of stunning. There are several things to say about them. Valiant, I mentioned this planar matching result of Castellan. This was used by Valiant as a foundation for a class of algorithms he called holographic algorithms, basically things reducible, often in very sophisticated ways, to counting matchings in planar graphs. These holographic algorithms, I think he believed for a while that this may prove that P equals NP, because these are far more sophisticated reductions and algorithms using cancellation in fancy ways. He was hoping that maybe it will be a way to find a strange algorithm for an NP-hard problem. And in parallel, people were studying models of quantum computing that are restricted. In particular, Tehal, DiVincenzo, and Neil were studying quantum computers that use only fermions. And it turned out that these two classes of algorithms, quantum algorithms using only fermions, and holographic algorithms of Valiant that have nothing to do with quantum, are actually the same class. And they are all reducible to determinant. So here the determinant shows up because of the fermions. On the other hand, Scott Aronson, his student at the time, Archipo, studied bosons and suggested that networks with bosons, actually very simple networks, can, in some sense, compute the permanent. So they don't exactly compute. So you want to really, I told you that quantum computing sits below sharp P. You want to get it as high as you can. So for sampling problems, you can do that. I'll not describe exactly in what sense, but it seems to be a very different behavior between fermions and bosons from complexity theory standpoint. But we believe, I think, that the efficient Church-Turing thesis says that not only algorithms and people are restricted to run in polynomial time or somehow efficiently, but nature also. So what's going on? I mean, how does nature knows what to do with the bosons? I mean, if permanent is what describes it and what they, their evolution, how does it work? I think it's a great challenge to both physics and computer science to make sense out of this. I mean, is this really the right explanation? I don't know. I talked to physicists who are interested. Scott got to this problem because of this paradox, and it's a very interesting question to me. I'll end with 5 minutes, very good, talking about approximating the permanent, another Boolean problem, approximating for non-negative matrices. Why? Because if you want to approximate the permanent in general, you have negative entries, that's NP-hard. Okay, so Valiant shows that, as I mentioned, computing the permanent is sharply hard, and approximating the permanent for non-negative matrices was shown in a beautiful and one of the most sophisticated algorithm we know by Jerome Sinclair and Vigoda to be very well approximated. It's a polynomial time approximation scheme if the matrix is non-negative. This is using the method of Markov chains, which I think is, as you know, is used for lots of enumeration problems. So that's an absolutely fundamental paper. I should say maybe that Jerome and Sinclair, when Alistair Sinclair was a student of Jerome many, many years ago, started this applying Markov chain techniques to and analyzing them for polynomial time, for matching at the time for permanent, at the time they could do it for very restricted classes of matrices, but persevering for, I guess, about 20 years, we know today that the permanent of any non-negative matrix can be approximated well, efficiently. But this is a probabilistic algorithm, Markov chain. You just around this Markov chain is a randomized algorithm. What happens if you don't allow randomization? Of course, we know what to do with assumptions, but I want without assumptions. So I give you a non-negative real matrix, and we looked at this about 25 years ago with Lina and Samornitsky, and we found a polynomial time algorithm that gives a poor approximation, but still non-trivial. An n factorial approximation is really easy. So this has e to the n factorial approximation, and it has two ingredients. One is the famous van der Waals conjecture that was resolved by Egoritshev and Falkman, and later by Gurvitz in a beautiful simpler proof that led to a lot of things I will not talk about. What is this conjecture and the theorem? If you have a doubly stochastic matrix, okay, rows and columns sum to 1, then the ratio, I mean the lowest permanent it can ever have is when all values are 1 over n. And then this number is about exactly e to the minus n. And the other ingredient in this algorithm is a reduction to the doubly stochastic case. I give you any non-negative matrix. If you can make it doubly stochastic and maintain by changing it with, you know what the value of how the permanent changes, then you can get this factor of approximation. And this algorithm that does this reduction was the basis of the paper I mentioned before, that allowed this geodesic algorithms, this non-commutative gradient descent and so on. At any rate, I want to mention that this e to the minus n was improved to 2 to the minus n, and I think that's the best known up to polynomial factors by Gurvitz and Samornitsky. The algorithm above does not even look at the matrix. Well, it does, I guess it does look at the matrix to reduce it to a doubly stochastic, but doubly stochastic matrix, I give it to you, say 1, it will be e to the minus n approximation. The algorithm by Gurvitz and Samornitsky uses the matrix in more sophisticated way, but still exponential. So my last open question is just beat it. I mean, find a sub-exponential factor approximation in polynomial time. That's one of my favorite open questions. Yeah, I mentioned this connection. So summarizing what we've seen, this study of these polynomials and the permanent in particular have been really a beacon of light on computational complexity and led to many fundamental definitions and results, and I assume will continue doing so. So I'll end with my slide. Srikant mentioned this book. He may not have mentioned this is free online, so it's free online. Thank you. Questions? Yeah.
Okay, I'll ask the first question. So you showed this construction, this realization of formulas by determinants due to variant, and it uses these funny constants, these ones, and this makes the construction non-homogeneous. Do we know something on the polynomials that you can represent using determinants, say with entries that are homogeneous linear forms?
Yeah, I don't know. I think that the reductions, I know there are several variants of this, and I think they become non-homogeneous, I think. Anybody maybe here knows different? I don't know how to make it. That's a good question. Yeah.
Thanks, Avi. So I guess my question is about this PIT algorithm that you mentioned, and you said that there's a non-commutative one that you have you can solve it in polynomial time. So structurally, is there a difference between the non-commutative and the commutative case?
There's a huge difference. There's a huge difference. Even the definition, you cannot talk about determinant anymore when you have a matrix of variables that do not commute. There are many definitions of determinant. I mean, monomials now have an ordering, right? So there are many famous ones, and they are different. What you should talk about is a question which is identical in the commutative case, namely, is the matrix invertible? In the commutative case, well, invertible well. In the commutative case, the answer is obvious in the field of rational functions over the variables. In the non-commutative case, the answer is the same, but what is this field becomes enormously complicated. The field of non-commutative rational function is a very sophisticated, complex beast. Many intuitions we have about rational functions from our experience do not hold there. In particular, for example, the fact that every element can be written as a ratio of two polynomials does not hold there. And there are many others I can talk about. So it's a very different one and seems more complex. In some sense, it was surprising that for this more complex problem, for which the earlier best algorithm was exponential time, we can get down polynomial time without randomization. On the other hand, you can say a non-commutative world is more restricted, more rigid, and maybe this is the source of why it became polynomial time, and we still don't know it for the commutative case.
So let's thank Avi again.